Hello, I'd like to talk about a programming technique that is part of what we are the essence of 104. It's called recursion. Now, to motivate this, consider that there are a lot of definitions that define something by first defining it for one or two cases and then bootstrapping on that, defining each case in terms of cases for lower numbers. The example I use is factorial. Factorial of 0 is defined as 1. And factorial of n is defined as n times factorial of n minus 1, for all n greater than or equal to 1. So factorial of 3 is 3 times factorial of 2 is 3 times 2 times factorial of 1, and so on down the line. Now, when we do a recursion, we have to have some final resting place. In this case, it's when we hit 1 or 0, depending on how you look at it. We're finished at that point. So let's see what this might do for a computer program. A program is recursive if it calls itself. Now, at first glance, that looks like it might be a problem. If it calls itself and then calls itself again and then calls itself, it looks like it might go on forever. But the fact that we have some place to end will stop it. We'll only call ourselves in certain cases, and we'll have a case that stops the whole thing. Now, I'm going to write this program. This is a rough way I'm going to think about writing it. I'm going to have the function factorial. It's going to get a variable that is an integer. And if n is 1 or 0, it's going to return 1. Otherwise, it's going to go exactly according to the definition. It's going to take n times whatever it gets back from factorial n minus 1 and return that. And so eventually, we will get the answer. Now, I wrote this and I have added some outputs so that we can see it. I'll bring it up and we'll look at it and then we can talk more about it. So let's see. Here it is. Excuse me. This little one wants to be involved, so I have to hold her occasionally. Now she doesn't want to. She wanted to come up, now she doesn't. I don't know. All right, let's look at the program. All I've done is say, input a small positive integer, and then I'm going to write out whatever I get by calling factorial of that number. Now the 1 I'll explain later. It's for the pretty output. And the program is exactly what I said it would be. If n equals 1 or n equals 0, return 1. Otherwise, return the value, which I defined as n times this. I had to do it that way because I wanted to write that out before I returned. So that's the program. Very simple program. The rest of this is so I can get it to write out what it's doing. Before I call the program, I tell you I'm calling it, and I'm telling you what the value of n is. So you see it up there, and you see it down here, and you see it down here. Now what's with this number, the second argument in here? I wanted to space these out. I wanted to indent each time I called. So what this is the number of tabs I want to use. The first time I don't want to write any tab it over at all. I want it on the left edge. But I call fact with 1. So when I write the first time I'm in this program, I'm going to write 1/\t, which is a tab, and then I'm going to write what I want to write. And then when I call the program again, I'm going to add 1 to tabs. So the second time it'll be 2, and the next time it'll be 3, and so on and so on. And I did exactly the same for the return. Every time I returned something, just before I returned it, I told you what it was I was returning. So I told you what value I'm coming back with. And I also indented them in the same way. Now let me run this. We'll try a simple number and then we'll go higher. I think I'll just try 4. So what it's saying is, I'm calling factorial 4. Factorial 4 is calling factorial 3. Factorial 3 is calling factorial 2. Factorial 2 is calling factorial 1. Factorial 1 is returning with the value 1. That was in the, right up here. That's from this line. Now, factorial 2 is returning with the value 2. Factorial 3 is coming back with the value 6. Factorial 4 is coming back with 24, and that's the answer. The funny thing about this is the number doesn't stop building up until we return. We just keep going down, and then when we get to the end, that's when we start building up the number. Now, I can't do this for very, very large numbers, but I can do it for 10. And you can see how it keeps going down, 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 and then it starts coming back. This is fairly typical a way a recursive program works. It goes down, it calls itself constantly, and then at some point it stops. And we start returning, and the value keeps building up as we return. Now, recursion is expensive in the computer sense. First, it takes a lot of time because you're always recursing. You're always calling. And calling functions take time. Plus, they take space. I don't think we want to go into all the details of why they take space, but I would tell you that it has to do with how I pass things to the functions and how I get things back. This program I would not use to do recursion because it's too easy in many respects. But there are many, many other programs where I want to do recursion because that's the way it's easiest to think about it. And for that, I'm going to start with another idea here. I think this is the end of this. Let me check. There's an output. Okay. Now I'm going to start talking about something called a binary tree. And to do that, I'm going to bring up another item here. Yes, right here. A binary tree is a solution for a problem we have. First of all, the concept of a tree is used in mathematics and in computer science constantly. A tree is just a data structure. It's just a way of looking at things, a way of organizing information. Tree is just a set of nodes. Each node contains some information and contains pointers to other nodes. One node is a special node. It's called the root. And the root is the only node that has no parents. It's the beginning of the tree. In analogy to the real tree, it's the bottom of the tree. We're actually looking at trees upside down here, because we usually portray them with the root at the top. And then, if the root has pointers to others, they are its children. So, in a binary tree, we're going to have two children. And we're going to say one goes to the left and one goes to the right. And each child, we'll say, has a parent. The node that points to it is its parent. The technical definition of a tree says that you can't go around in circles. If you can go around in circles, you have what is called a graph, which is a generalization of tree. But for a tree, I can't start at A and by following the children get back to A. That's just not allowed. Every node but the root has exactly one parent. And interestingly, every node begins a tree. It can be looked at as a tree of one node or as a tree with all its children. I have some examples I got off the web. You can see how they're described. This is not a binary tree. It's a tree that has 3 children in some places. But we could have as many as we want in some applications. And here's one, same kind of thing. It's not a binary tree. The problem that a binary tree solves, it begins to solve. There are many implementations of trees that get better and better as people come up with more ways to work them. We need to be able to organize data so that we can search it, we can add things to it, and we can remove things. A classic example of this is a telephone book, where you have the name, the address, and the telephone number of a person, and you want to be able to add people and take out people. So you need to be able to dynamically change the information you have. The problem is that we also need to be able to search the information. By the way, most of this material is from a part of computer science called databases. And databases are one of the hottest areas in computer science. Every company essentially has a database of its clients or of its products. And databases, we have 2 courses on it. It's one of the specialties of computer science. Now, I'm going to think about the problem a little. Somewhere earlier in the semester, we talked about a binary search. That was a pretty good way of searching a list. Much better than starting at the beginning and going one at a time. That was where we jumped in the middle and decided which side we should look at for what we're looking at. The list had to be ordered, which was fine. We could do the ordering. Now, the problem is that the entries must be in order. And in most applications of a list, they have to be in consecutive order. Well, that poses a problem. Suppose we have the list here with Adams, Cooper, Faraday, Harrigan, and Jones. Don't ask me where I got the names. I don't know. Suppose we want to add Edison to the list. Oh, Edison goes between Cooper and Faraday. But we've got no room between Cooper and Faraday. So we have to move. We essentially have to move the entire list above Cooper up one to open up a place for Edison. And that's time consuming. You might say, well, why not go the other way? Well, the problem is we know the list begins here. We don't want to change where the list begins because our programs are pointing to the beginning of the list. So we really can't go backwards. The same thing is going to happen when we try to remove something. We're going to have a hole where it was, and we're going to have to move things down to fill it in. And that can take a lot of time. So what do? We've got to find a way that we can store the elements so that we have plenty of room to put more things in. And at the same time, we can search them as if they're in a binary list, in an ordered list. And enter the star of our show today, the binary tree. Now, here's a binary tree I've made. The top node is the root. It has McDonald in it. It has two children, Faraday and Stevens. Faraday has two children, Cooper and Harrigan. Stevens has two children, Ocasio and Urey. And Urey has two children, Thomas and Williams. Now, Harrigan alone is a tree. It's one element tree. Everything from Faraday down on this side, that's a tree. It has, if we look at Faraday as the root, forget about the rest of the tree. It's a subtree. And that's very important when we're doing our recursion. The point is that when we look at the element of a tree, we can look at its children, and each of the children is a tree, or begins a tree. It's the root of another tree. I wrote that there a little. We're going to call the children our child and our child. That's very traditional. Now, I put these in a funny way. I haven't told you yet. I was a little bit careful. Look at everybody. Look at the left child of McDonald. It's Faraday. The value of Faraday is less than the value of McDonald in the alphabet. Look at Stevens. It's on the right child. Stevens is greater than McDonald in the alphabet. Now look at Cooper. Cooper is less than Faraday, and therefore Cooper is less than McDonald. Harrigan is greater than Faraday, but if you'll notice, it's less than McDonald. So everything that starts at the left child here has a value less than the value in its parent. And the same thing is true in the right here. McDonald is less than Stevens. Stevens is less than Urey. Urey is greater than Thomas, but Thomas is less than Stevens. And Thomas is less than McDonald. That's what makes the binary search tree work. What we're saying is when we put things in this tree, our job is to make sure that we put things to the left of a node if their value is less than the value in the node, and to the right of the node if their value is greater than the value in the node. That's how we're going to put things in. So I think that is what I wanted to say about that. Now, this is not important. In fact, it's been superseded. And I think this may be, I'm not sure if this is, last year's program, so I better get rid of it. I'll show you this year's. We'll get rid of that entirely. And I'll save this. And now I'm going to go back to the other one that I was looking at a few minutes ago, the notes on recursion. So I want to create a program to make a tree and then to search the tree. So let's go over to here. I'll get rid of this file. And I'll bring up the binary tree file. As with the linked list that you're doing with the waiting line, we first have to define the elements, the nodes that are going to go into the tree. So I'm defining a node as having two things in it: a name and a telephone number. But the telephone number is a string because I want to be able to start it with 0 if I have to. And there are two other things in the node. There are the pointer to the left child and the pointer to the right child. And the left and right child are both nodes. By the way, you can't put comma right child here unless you put the asterisk in front of it. It's easier to put them on two separate lines like this. Now I'm going to try define the class that is a B tree. First of all, it has a generic constructor. I define it as the just B tree. It has a function that adds a node. That function gets the name and the telephone number. Then it has a function called find the telephone number. It gets a name and the tree to look in, because I'm going to use it recursively. So I want to have it so I can change where it's looking. And then I think I had one more. Yes, as I was writing the program, I needed to be able to get to the root of a tree. So I gave myself another function in the public area that says return the root. As usual, I called it get root, which makes sense. Now, what's going on here? The private part's very simple. It's essentially the root. It points to the root, I should say. It isn't the root itself, it points to the root. And you'll notice I initialize these nodes to null. That made it so I didn't have to do it every time I created a new node. It's a nice way to do things. It's a standard way. It's a good way of doing things. So let's go and see how we write it. Now this is going to get complicated. All right, I want to add a node. So let's see if I can go back here, see if I can talk about this somewhere. I have several cases, I think is the best way to look at it. Let's suppose that I just have the Harrigan here. Oh, no, let's suppose the entire thing's empty. Well, if the entire thing's empty, all I do is create a node and put my values in it. So, one step, if the tree that I am searching is empty, create a node and have the tree point to it. Now that's a very easy case. Pardon me. That blur came by. Now, the next question would be something like this. Let me see if I can make an example quickly. Hierarchy will do it. Okay, there we are. I'm going to have a case here where I have Jones, and I'm not going to have anything here, so this is going to be basically destroyed. And I'm going to get rid of this, and I'm going to have right here nothing. This is going to be no. Now, it's hard for me to show it as no, so that's the way I'm going to have to do it. And over here, I'll have Smith. And there's nothing down here yet. So that's what I'm starting. And now my goal is to add. I better get down a little further, or I'm going to take that off the edge of the world there. I'm going to add, let's add Cooper to this tree, starting at Jones. Now we look at Jones. Cooper is less than Jones. It belongs down the left tree, the tree starting at the left child. I wish she'd find another way to get up there. Pardon me. Every time she does it, she has a good chance of knocking out my sound, but she didn't do it this time. So now, if you look, there's nothing to the left child. The left child is no. So I create a new node and make it the left child of Jones. And I will get the obvious, put it in here, put V, and I think I made it Cooper, so now I just put Cooper in here. And everything's fine. Now let's suppose I've got that in, and now I want to add Williams. Well, I look. Williams is greater than Jones. It belongs to the right of Jones. And here's where the recursion could come in. I didn't use it in this case. I used it for the next part. What I'm going to do now is I'm going to say, okay, since there is a node as right child, I will now try to put Williams in the tree that starts at Smith. And I will see when I do that it belongs to the left. But to the right, pardon me. But to the right, there's nothing. So I'm going to take this again. Pardon me. And let's see. I need to get the text plane. I need to get somebody under Smith. And this is a problem in this particular setup because it won't let me do it the way I want it. But I'll manage. I'm going to call this null. And now I'm going to put Williams down here. And that's where it should go. But I might have to keep going and going down that line there. Now I could do that recursively. But for this first one, I decided to do it with a loop. So let's look at how I did this. I said, the first case, the root is null. The root is the root of the tree I'm adding to. It's the tree that is pointed to, or it's the tree I want to put it in. If the root's null, create a new node, have root point to it, and put the name and tally in it, and you're done. Else, now we're going to start walking down the tree. This is the same as we walk down the linked list. I'm going to have a variable called pos, which will start off as root. And I'm going to have a Boolean to see when I get done. Now, as long as I haven't figured out where to put it yet, I'm going to ask the first question. Is the n, the name, less than where the current node points to? The first time I do it, it's the root. So is it less than the root? And is that node, which in this case is the root, does it have a child in that direction? If it has a child in that direction, I just have to keep going down that side. So I move pos, the current place I am, down to the left child. Else if it's less than, and there's no, and there is a child there. In other words, if it were null, there'd be no child. This case, there is a child. No, other way around. In this case, there's a child. I'm going down the follower. In this case, there's no child. So I create one. And I put it in where I want it to be. It's going to be pointed to by, it's going to be the left child of the current node. Pos points to the current node. So pos points to left child is where I'm hooking the new one. And I'm done. I have the same thing on the other side, where I basically have to look at it the same way, and I have the else the same way. It's not trivial, and you're going to have to look it over a few times, and I have no doubt I'm going to have to go through it in detail again, but this is like a first run-through to get you some idea of it. Now that one I wrote non-recursively. The next one I wrote was to find something. Well, this one was easier to do recursively. So what I said is, I am going to look in the tree that P points to. And I'm going to find N in that tree. If P is null, there is no tree. So obviously N isn't in there. So I'll return not found. However, if n exists, I know now that p exists. So it has a p name. It has a name. If n equals that name, then I return the telephone that corresponds to it. Else, if n is less than it, then n should be on the left side. So why don't I search the left tree? I'm taking the same thing to search for, and the root of what I'm searching in, the new tree, is the left child. That's the pointer that is going to be, that's the root at this point. And I do the same thing for the right child. And it's real neat because they keep, I just keep going down until I either get a point where it's not found or it's found. Now, to test it, I put a few things in, and then I did a test of it. I'm going to do this. I'm going to debug this so I can show you what is happening. I think I am anyway, yeah. Now, the debug says I can look at the various variables I have. X is a tree. So what is X? It has a root. Let's look at the root. The root has a name, Joe, and it has a telephone number that's connected with Joe, whatever that is. Excuse me. Can't get it to go down. Now, this root also has a left and right child. The left child has a name Al, doesn't have any children. The right child has a name Mike. It doesn't have a right child, but it has a left child. Mabel's left child, and she has no children. So you can see here the tree is set up properly. That's the first thing I checked. And the way to check it without writing a routine was to actually go and debug it and look at it. So again, EX is the tree. Root is the pointer to the root. Root has a name, or what it points to has a name, pardon me, and it has a telephone number, and it has a left child and a right child. The name, in this case, is Joe, and telephone's 123. The left child goes down to Al with a number, and that's and the right child goes to Mike, who actually has a left child, Mabel. And the bottoms of the trees are where we get nulls, both on the left and the right. So that's one way that we can look at it and see that it works there. Now, I could go through and do it more and more like this, but I'm just now going to run the program to its end. Well, I thought I did, but that should do it. Now, I'm going through the whole thing, unfortunately. I'll show you the output in a second. Here we are. Let's see, I was first looking for, I gotta go up here, pardon me. The first person I looked for was Al. Al has 674 as his number. The second person I looked for was Wally. Wally's not in the list. The third person I looked for was Mabel. Mabel has 918, as you see there. Now that's the program. That program shows the recursion. That part was written recursively. Actually, it's much easier to write it recursively. In fact, I might have been better off writing the add recursively. But I did it non-recursively just to show you it could be done both ways. So that's the story about trees, binary trees. When you get to next year, and we are in CS225, you will find that there are more trees than you could believe. There are B-star trees, and there are AVL trees, and there are every kind of tree you could think of that sort of is a binary tree, but has more things going for it. But right now, we're not going to go much deeper than this. You'll have some work to do with the tree. You'll have homework for it. But you'll have to look at this program carefully, and hopefully I'll be able to give you some more help on it. We'll see you later now.